and then your final exams in 2 weeks. It's like summer just feels a little bit too fast, right? Okay. Anyway, here we are, week 4. It's Wednesday. I have all the dates wrong. I think it's like because I'm reusing notes from like last year where the classes were on Tuesdays and Thursdays. So I apologize if some of these things are mixed up. But anyway, yeah, it's week 4. For this class, I feel like there's a lot that I want to cover, and so Monday is a holiday, so we don't have class, but I feel like we're gonna, like, if we lose that lecture, we're gonna miss too much stuff. So I'm gonna have a lecture on Friday, okay? Friday at noon. It will be online. I'll send out an announcement. I know it feels like there's already so much stuff, and believe it or not, I am trimming stuff out of the 10-week course, right? So I have, the normal fall quarter or whatever, winter quarter, spring quarter is when we teach 102B. And, we have 10 weeks. We have, 3 sessions a week during the regular school year. And so I actually cover more stuff then. So I've actually like trimmed some stuff down, and I know it still feels like so much. And and I just feel like if we lose Monday's lecture because of the holiday, like I feel like we're gonna miss a little bit too much. So we're gonna have a lecture on Friday, and anyway, so I'll cover more stuff. But I hope you feel like you're learning stuff, and that the stuff we're covering is interesting, at least relevant and stuff. And I know a handful of you are also in my 101C class, and there's like overlap, except in the 101C, we're approaching it from more of like a applied standpoint. So I don't really get into the algorithms themselves, but just like, how do you implement this in R if you actually want to use it in a production setting? And so if you're in both classes, I hope it's a good experience. And even if you're just in one class, I still hope it's a good experience. We introduced classification methods on Monday. So on Monday, we looked at the Bayes classifier. We also looked at the naive Bayes classifier. And that uses Bayes' rule, and it returns kind of a probability on what it believes an observation, which class an observation might belong. The probability that an observation would belong to a certain class is what I'm trying to say. So that was the Bayes classifier. We're going to look at a couple more classification methods. We'll look at K-Nearest Neighbors, which is kind of a very common classification method. It's pretty simple, and so we'll explain how it works. We will also look at the support vector machine as a classifier, which sounds like such a fancy term, but really it just comes down to like draw a line to separate two territories or two regions. That's the support vector machine. And the math behind the support vector machine gets really kind of complicated and wonky, and we'll just kind of like touch a little bit on some of the math behind the support vector machine. But that's what we'll take a look at today here. Okay. So anyway, today there's a lecture view quiz for today, and then we're going to have Friday's lecture, and there's a lecture view quiz for Friday. I'm going to leave both today's lecture and Friday's lecture open till Wednesday of next week, because I like to leave them open until the next lecture. And so if you're watching the video and you watch it after Friday, both the lecture view quiz for Wednesday and Friday are open. So make sure you are answering the correct view quiz, all right? So, make sure you don't put today's answers into the Friday quiz, and don't put Friday's answers into the Wednesday quiz. I'm trying to give you a warning when you open up the quiz, like in big print, it says this is for Wednesday and stuff, but just make sure. So again, this is Wednesday's lecture view quiz. Okay, let's see here. Okay, so let's start by looking at K-nearest neighbors. The algorithm, quite simple. You have training data. All of your training data is already labeled, right? So you have answers, and we use the training data to make a prediction for the test case. The way we make a prediction is, we don't have like a model. There aren't parameters for us to really estimate, okay? There's not like we need to figure out weights and we multiply stuff or anything like that. The way we use the data is we say, okay, here is our test case, and let's find other points in our data that are similar to this test case, okay? And we do that by finding the nearest neighbors. So that's kind of just like here's our test case. What other values in our data look kind of like this? And if the values that are similar to this test case all belong to a certain class, okay, then we say, okay, we're gonna predict that this person, belongs to this class, right? So for example, let's say you're trying to classify, I don't want to get in trouble for playing up to stereotypes or something, right? But you just imagine like what your typical engineering student might look like, right? Like a computer science student versus like a communications major, right? So just picture in your head if somebody said, okay, give me what you imagine a computer science student to look like, right? And then give me what you imagine a communications major to look like or something, right? And then here you have a new student come in, okay? And you have to guess, is this person, and I tell you, this person's either gonna be computer science or communications. And then you ask questions like, okay, what is, I don't know. You create a profile and you say, okay, who in my data is similar to this individual? Okay, who is similar to this individual? And so maybe you find 5 people who are very similar to this individual, and then out of the 5, 4 of them are communications majors and 1 is a computer science student or something. Then you say, okay, well, because out of the 5 people who are very similar to this individual, most of them were communications, we're going to guess, if we had to guess, this student's going to be communications or something like that, okay? And that's kind of how K-nearest neighbors works, okay? And so how do we say who is similar? Well, the way we're going to say who is similar is we measure the distance from the test case to the other data points in our training data. We use Euclidean distance. So we are going to look at your x1 variable, and we say, what's the difference between x1? And to get Euclidean distance, if it's x and y, you do, this point minus this point, you square that difference, and the y minus y, you square that difference, and you add them up, you square root of everything, right? Euclidean distance, we're going to measure the Euclidean distance from our new test case to basically every single data point in our training data. And from there, we get distances to all of the points, and we say, okay, these are the 3 points that are the closest, or the 5 points that have the smallest distance. Okay, we're going to say the ones that have the smallest distance are the ones that are most similar. And so, yeah, we get distances to every single training point. We sort those, and we say, okay, the ones with the smallest distances, those are the nearest neighbors. Those are the ones that are closest. And then out of the ones that are the nearest neighbors, basically they vote. They say, I'm class A, I'm class A, I'm class B, I'm class A, I'm class B. And you take a vote, and the majority, or whichever class has the most representation in the nearest neighbors, that's the one that wins, and that's going to be how you classify this point. How do you pick how many neighbors to use? We generally recommend cross-validation. You would say this is a tunable hyperparameter. A hyperparameter being, this is kind of the one value that you have to choose as the researcher. And so what you might do is you might do cross-validation, and you'll say, okay, if I use the one nearest neighbor, how many times do I get it right? How many times do I get it wrong on my validation set? If I use 3 nearest neighbors, how many times do I get it right? How many times do I get it wrong? If I use 5 nearest neighbors, how many times do I get it right? How many times do I get it wrong? And based on that, you get kind of an estimate of how accurate your model will be based on a different number of K, and that's how you would kind of choose which K to use. Okay. So one thing to note is that for large data sets, KNearest Neighbors is often not recommended because it becomes so computationally expensive. Okay, because you have to measure the distance from your point to every single other point in your data. Now, I'm going to show you some examples, and the examples will be in 2 dimensions. And our brains and eyes are trained already to recognize distance in 2 dimensions very easily, right? I can look out and I can say, okay, these 2 people are seated near each other, and these 2 people are seated far from each other. That's very easy for us to do. And so you might feel like, well, why do you have to measure distance to all the training data? Well, as soon as you go higher than 2 dimensions, say you go into 5-dimensional space, okay, now we can't really picture this, and now we really don't know what the nearest points are. So once you get into a higher dimensional space, it's really hard to know, okay, what are the 5 nearest points? In 2D, you look at a picture, it's really easy. These are the 5 nearest points, okay? But in higher dimensional space, identifying the 5 nearest points is no longer easy because we don't have, our brains can't have a hard time picturing what 5-dimensional, I have no idea how to even draw this, okay? So you have to measure the point to every single point in your data. And so if you have 1 million data points, you have to measure 1 million distances, and that could be computationally expensive, okay? The other thing to note is that when you are measuring Euclidean distance, we are expecting our numeric values to be, our variables to be numeric. Our variables are expected to be numeric. Okay, so if you have categorical variables, it's really tough to do K-nearest neighbors because let's say you have, I don't know, some, like if you're looking at the iris data or something, but you also had like the color of the flower. This flower was purple, and this flower was red, and this flower was blue, okay? How do you measure distance there? And that's, I don't know, okay? Measuring distance between colors is tough. Now, we have, because we have computers that represent colors and stuff, we do have a way to kind of turn colors into RGB values, which are suddenly numeric. And so you can take a color and make it a 3-dimensional numeric, a series of 3 values, and you might be able to measure distances that way. So I guess in some of these things that were traditionally thought as categorical, like color, could end up being turned numeric. So maybe that's okay. But some of these other things, like how do you measure distance between, say, what if one of your variables was the country that somebody is from, okay? And then how do you measure distance between countries? And I don't think we would use geographic distance, right? We wouldn't say okay, Canada and the United States may be culturally fairly similar, actually. So that kind of geographically it works out. But then I don't know. I don't know if geographic distance is the best way to measure distances, right? I don't know, similarities between countries. It's really, right? Because technically, Russia is really, really, really close to the United States, right? There you just cross the Bering Strait. But I don't know. Is Russia similar to the U.S.? I don't know. But anyway, so categorical variables K-nearest neighbors don't really work very well for it. You can try to turn them into dummy variables and things like that. And another note, because you are using distance, you'll want to normalize all of your variables as well. You want to kind of put them all on the same scale. So again, if something is measured in centimeters and a different thing is measured in meters, a distance of 10 on centimeters is actually less than a distance of 0.5 in meters, right? But you wouldn't know that if they're on different scales. So you want to normalize everything so they're all kind of on similar scales. Sometimes with K-nearest neighbors, you get ties, and then it becomes like, how do you classify this, okay? Well, one thing is if you only have 2 classes, just pick an odd K and you won't ever have a tie, okay? So if there's only 2 classes, pick an odd K, you won't have ties. But if you have more than 2 classes, you can end up with a tie, okay? So you could, if you have 3 classes and you're doing K equals 9, you could have 4, your 9 nearest neighbors, 4 could be class A, 4 could be class B, and 1 could be class C. Now you have a tie. How do you choose between A and B? And there's no set rule. There's different ways to do it. One, you can just say, okay, well, I don't know, unclassified, okay? You could switch to the 1 nearest neighbor and you can say, okay, well, out of the 9 points, we had 4A, 4B, and 1C, but the nearest neighbor was class B, so we're gonna count this as class B. And generally you won't have ties for the 1 nearest neighbors. In some unusual circumstances, or if you have a discrete, if your numeric variable is discrete, you could have a tie in distance. That is possible. But usually we want to, basically ties are bad, so we want to avoid ties. You can also say, you can select randomly. So if you have 4A, 4B, and 1C, you can just flip a coin and choose between A and B. Or you can say between A and B, which one has the 1 nearest neighbor? And that's not necessarily the one in the 1 class. Because if you had 9, it was 4A, 4B, and 1C. It is possible that the 1C was the 1 nearest neighbor. So the 1 nearest neighbor is not necessarily the nearest of the closest ones. So these are strategies for resolving ties. I think in your homework assignment this week, you have to code up K-nearest neighbors, and so you'll measure distances from each of these things. Okay, so I will show you kind of how K-nearest neighbors works. I have intentionally hidden my code, so because you have to write it for your homework. Okay, so I've intentionally hidden the code behind the next few slides. Okay. So here is going to be our data. This is just randomly generated data. I just said generate some random multivariate normal data. And this is what we have. We have red and we have blue. And I'm going to put in a test case. Okay, so I'm going to put in a test case right here. And we are going to do K-nearest neighbors. And so the first step is to measure the distance from this point to every single other point. And again, in 2 dimensions, our eyes can easily recognize that these are the kind of the nearest neighbors. It's very easy for us. But again, higher dimensions, it's really hard to judge which points are the nearest neighbors. So here we are measuring the distance from our test case to every single other point in the data. And now I'm going to say, okay, what is my 1 nearest neighbor? Okay, the 1 nearest neighbor is going to be this point right here. And so I've sorted them by distance. This is the 1 nearest neighbor. And I've drawn a circle so you can see that there's no other point closer to our test case than this. And because this 1 nearest neighbor is red, we are going to classify the test case as red. Here I've gone up to the 3 nearest neighbors. So this is the 3rd nearest neighbor, which is blue, and these are the 3 closest points. And so I've drawn a circle again, and you can see that these 2 points are closer, everything else is farther away. And out of the 3 neighbors, 2 are red and 1 is blue. So this one would get classified as red if we used K equals 3. If I go up to k equals 5, these are the 5 nearest neighbors. Okay, again, a circle drawn at the 5th distance, and we can see there are 4 points that are closer, and that's the 5th one. And out of the 5 points, 3 are blue and 2 are red. So if we used k equals 5, the same test point would get classified as blue. Okay, so depending on what k you use, you might end up choosing to classify this as red, or you might choose to classify it as blue. So that would be the 5 nearest neighbors. Here it is with 7. With 7 nearest neighbors, we have 4 that are blue and 3 that are red. We have a point that is very close, but apparently this one is just a touch closer. But we still have, it's 4 versus 3. This would get classified as blue, and that's kind of how it works between 1, 3, 5, and 7. And you can just imagine this going on to a greater number of neighbors here. Here is another test case. Test case at 1. 1 is the test point. Again, we're going to measure the distance from this point to every single other point in our data set. And we start off with what is the 1 nearest neighbor. The nearest neighbor is red. This would get classified as red. Okay, let's try the 3 nearest neighbors. These are the 3 nearest neighbors. 1 is blue, 2 are red. We would classify this as red. Out of the 5 nearest neighbors, 2 are blue and 3 are red. So at 5 nearest neighbors, this is still red. At 7 nearest neighbors, 4 are red, 3 are blue, so that we would still classify this as red. Okay, so in this case, this test point is pretty much going to be red. Okay, in all kinds of circumstances, whether k is 1, 3, 5, or 7, or you can pick a higher k, and that's what we would have. Let me go ahead and give you your first view quiz answer, which is the letter D. D as in dog. D as in dog for your first view quiz answer. Week 4, Wednesday, yes. Okay, D. D as in dog. This is just some code that I copied off of a Stack Exchange post for how do you draw kind of boundary regions. And so the way this works, so this is the training data is the same. So if I scroll back to here and you just like look at these points, the blue points and the red points, these are the same blue and red points, okay? I don't know if you can see that. But now I have this huge grid of red and blue dots overlaying our diagram. So what is going on here is I asked the computer, I said, start over in this corner and go all the way over to this corner, okay? Basically, from the smallest x and, the extreme x and y values, create a plot. And it creates a huge grid, and it basically tested every single dot here, okay? So it said, okay, for this dot, and if we chose the 1 nearest neighbor, how would it get classified? For this dot, if we chose the 1 nearest neighbor, how would it get classified? And so it went through this entire thing, and it said, at every single one of these points, what is the 1 nearest neighbor? How would it get classified? And so some got classified as red, some got classified as blue, and then we drew kind of a border between all of these, the red and the blue boundaries here. And so this is kind of for this training data, for these data points that are in our training data set, this would be the boundary that gets drawn between blue and red. And you can see, for points between the blue and red, right, if you're just a little bit on this side, the red dot is a little bit closer. Otherwise, on this side of the boundary, the blue dot is closer, okay? And then similarly, for here and here, the red dot is closer, the blue dot is closer. For here and here, it's kind of between these 2 points here. And over here, this red dot is closer. Over here, this blue dot is closer. Okay? And so we get kind of this border here. Okay. Same thing. We can say, okay, what about k equals 3? And so again, we have this huge grid of points. I asked the computer, test this out for every single one of these points. Choose the 3 nearest neighbors, and how would this classify? All right. And so for dots right here, these are the the three nearest neighbors are these three. And for all of these kind of points, they get classified as blue. As soon as you kind of cross over to here, okay, now your three nearest neighbors are going to be these two red points and this one blue point here, okay? And so these points get classified as red, okay? And this forms kind of the boundary between red and blue. And here it is for k equals 5. Here it is for k equals 7. And what is going on here is as you increase your k, you get a little bit more bias, but less variance, okay? As far as the boundary goes, or how these things get classified, the more k, so again, the bias variance trade-off, okay, larger k leads to more bias, less variance, okay? Smaller k will lead to less bias, more variance. But over here with k equals 1, you will have really like way too much variance, right? Because if we just picked a different random set, and if we didn't have this red dot here, okay, just because of randomness, if we didn't have this red dot, then probably all of these points would get classified as blue, okay? So it really depends on just like what kind of little random flukes of data do you get, right? So because maybe the true region is red is over here and blue is over here, but because of randomness, sometimes you get a little red dot over here. Sometimes you might get a blue dot over here. And with k equals 1, any of those kind of weird random points that pop up are going to influence how it goes. So as you have a larger k, just little odd points that pop up here and there aren't going to influence the classification as strongly. So it's a little bit more robust against odd little points popping up. But what that also means with a larger k is that the border between regions, is harder to move and less flexible. And so the true border might be, a little bit more flexible between the red and blue regions, but it's harder to kind of influence that. Now, just again, because of the random data and the random locations of the data, you're still going to get some jaggedness, but again, the overall, how easily is the border influenced by the random points. With k being bigger, the border is less influenced by individual points. Here it is at k equals 7. Here I'm going to add more data, okay? So here is just more values, red and blue dots here. And we will try drawing borders for this data as well. So when you do k equals 1, you can see like this one little dot, this one little blue dot out here forms its own enclave or exclave, okay? It's kind of these regions out here, okay? This one little dot out here in red now kind of has formed its own little red territory around itself. And if we were to judge this, okay, I think we would look at this and recognize, okay, this is just like a weird red dot, and this is not actually something that should get classified as red. Points out here, okay? This is probably just like a weird little blue dot, shouldn't really get classified as blue. All right, this part, we don't have a ton of data, so it's hard to figure out what that region would be, but I think we would feel very confident that this part is going to be blue and this part's going to be red, and that, sure, you get one little dot ends up out here, but that doesn't mean this area should suddenly be blue, and that's kind of what we're seeing here with k equals 1. So you have just individual random points really influencing how the borders get set up, okay? As we increase the k, so here I've got k equal to 3, now those individual points don't influence it as much, but again, you have some slightly odd situations here, okay? These two blue dots and this one red dot kind of form this odd region where this area gets classified as blue. And then, again, these 3 red dots and the blue dots and whatever, kind of form this odd region where, these points get blue and these points get red and stuff. But that's with k equals to 3. And again, as we increase the k, the influence of each individual point goes down, and the border gets, a little bit more, I don't know if solidified is the right word, but just a little bit more defined here. So here it is with k equal to 5, and so now we see, these individual dots being less influential. Here it is with k equal to 7 and k equal to 20. This is kind of the border that ends up getting formed. I have okay, so there's a weird artifact here, and I probably shouldn't have done k equal to 20, 20 being an equal number, where you can have ties, and so I think we're getting some, I think the border's getting drawn a little bit. I should have picked 21 so we don't have ties between red and blue. But you can see, with k equal to something a lot higher, 20, 21, now the border is kind of a little bit more robust against any individual outlier dots here. I should make a note of that. Set k equal to 21 rather than 20. Okay. Have I given you any view quiz answers yet? I gave you one. Okay, the first one. Okay, well, I guess I'll go ahead and give you your second view quiz answer, which will be the letter B. B as in bear. B is our second view quiz answer. All right, so that is KNearest Neighbors. You have to code it up in your homework, and hopefully you'll get a decent understanding of how that algorithm works. All right, let's talk about support vector machines. Now, the name support vector machines, it just sounds cool, right? But it's not super, well, it is cool, but it's also like, what we're doing is not really a mystery here. We're going to start off by doing what's called the maximum margin linear support vector machine. What a mouthful that is. Basically, the maximum margin linear SVM is, can you draw a straight line that will separate one class from the other class, right? And that's what we're going to try to do. And so, but you can only do this if your data is linearly separable. So if you can only really do the calculations if you are able to draw a straight line that separates one class from the other. And the idea here is you want to find basically parallel lines. So in 2D, two-dimensional space, which is, I'm going to show you points in 2D, we will draw two parallel lines. But in a higher dimensional thing, like in 3D, we would have two parallel planes. And in higher dimensional, like 4-dimensional space, you would have the linear equivalent, which would be parallel hyperplanes. Again, hard to picture, but in 3D, you would have basically a linear thing in 3D is just a plane, just a flat sheet, and you have two things that are parallel in 3D. In 2D, it's you would have two parallel lines. And so we'll start off with the 2D thing because that's easy to draw. And you want to try to find parallel lines where you can maximize the width of, basically, like you're drawing railroad tracks and you want the track as wide as possible. That's the maximum margin part. We want to make the margin between the two lines as wide, or maximize that width, okay? And linear for straight, and we want these parallel kind of hyperplanes there, all right? So I'm going to just start off with a very, very simple data set we've got some blue points, we've got some red points, and we want to separate them. And I think the blue points are drawn with a red negative sign. I'm sorry, blue are drawn with a positive plus sign, and red are shown with a minus sign. But these are basically just dots here. And that's because when we do the math, we're going to say these ones are positive and these ones are -1. And so we want to draw some parallel tracks. And so I think visually we can kind of see. I'm going to come over here. Like, if you had to draw kind of some parallel train tracks, I'd want to draw something, a parallel track here and here, or maybe here and here. And so something like this, right? But I will show you like parallel lines that could work as a border, but these are, this is not the correct one, because the width of these parallel lines is not the maximum possible, right? So this serves as a border between blue and red, but if you say, okay, what is the width between these things, we can certainly see some bigger ones. So, if I just pick a different angle, we can see, okay, here we get a pretty wide margin, okay, just by angling the border between here and here. We can say, okay, this distance here, the perpendicular distance is pretty, what is this? Okay, so this is the distance here, and are any of the other margins as big? And oops, this one's also pretty good, but if you measure it, it's not. If you measure the perpendicular distance, it's a little bit less than what I've chosen. Okay, so of these different options, and again, you can also draw a line as extreme as this, but we can see clearly that margin is also much more narrow, right? So technically, all of these linear boundaries perfectly separate blue from red, but the one that we're going to say is the best one is one with the widest margin. Okay, but technically this separates blue from red, and this also separates blue from red, but we're going to say the one that's best is the one that has the widest margin. So that's what we're going to do. Okay, so how do we so there's some math that goes behind this, and it ends up being something called quadratic programming, which I never actually learned how to do, and then I was going to try to learn how to do it like on my own, reading some stuff, but I couldn't find a good resource. So I don't actually know how quadratic program. Have any of you done quadratic programming for like optimizing something? Okay, yeah. Maybe linear programming. Have you? I did linear programming for optimizing something. That was like way back in undergrad. And I would be hard pressed to remember exactly what we did, but I remember seeing linear programming. But then I tried to do quadratic programming. I was like, oh, I don't know what's going on here. And then, funny enough, like our textbook, when you read it, like, okay, it comes to a point where it's like, okay, we're going to do quadratic programming, and we're not going to explain it. Just know that it works. So I was like, okay, well, our textbook's not going to bother explaining, so I'm not going to bother explaining. I guess it works, and we'll just have to accept that. But we'll at least get to the point where we can do the quadratic programming, and apparently we just have to say, okay, at this point it's quadratic programming, and it works. So it's a bit unsatisfying for me. I don't know how unsatisfying it is for you, also, but apparently it works, and it's well implemented in a bunch of these kind of algorithms here. So again, for support vector machine, what we want is we want to pick that boundary. We want to pick that line that's going to maximize the margin between the two parallel edges, those two parallel hyperplanes, lines in two-dimensional space, planes in 3D, hyperplanes in higher dimensional space. And the margin is defined as the perpendicular distance from that decision boundary, which is kind of technically this line in the middle, to the closest points. So if we say this is the decision boundary, this is the perpendicular distance to the nearest point, and this is the perpendicular distance to the nearest point on each of these sides. And we want to find that the one that maximizes it. These the closest points to that decision boundary are called the support vectors, right? And they are called support vectors because technically once you have determined that these 3 points are the points that define this boundary, okay, you can add or change any of the points out here. You can add more blue points. You can put points really close to the boundary out here. It's not going to affect the location of the boundary. You can put more red points over here. It's not going to affect the location of the boundary. You can or take away any of these points. As long as you don't touch these 3 points, or you don't put any points that are closer to the boundary than these 3 points, then these 3 points will be what define the boundary, and that boundary is going to be defined here. And so these, if you think of points as vectors, which is another way to think of these locations, right? Especially in higher dimensional space, we can say, okay, this coordinate can be treated as a vector. These are the vectors that support this boundary. These are the support vectors. That's what they are. That's what they're called. Okay. And so what we want to do is we want to, let me move that here. We're going to say, okay, these are the 3 points, and this margin, which is perpendicular, which shows the perpendicular width here. We want to maximize this margin. So in this case, if these were the support vectors, this would have a different margin here. So we want to kind of maximize this margin mathematically. And so I've taken this straight from our textbook. And, we have the training points. Okay, each of these points is a length 2 vector, all right? And so this is, x1 and x2 and whatever. These are two-dimensional vectors, and they have a label. And right now our labels are either plus or minus to kind of indicate the 2 sides. Okay, and so our labels T are either +1 or -1. And we want the maximum margin, SVM, that divides the group of points so that all the pluses, T equal to +1, are on one side, and T equal to -1 is on the other side. And we want the distance from the hyperplane to the nearest point is maximized. We want the distance from this boundary to this point maximized, the boundary from this boundary to this point also maximized there, okay? And so when we think about what is the boundary, the boundary is the set of points X so that we have this vector, a vector that's perpendicular to that hyperplane, so that w times x minus b is equal to 0. So let me try to explain. Okay. I don't know if this. All right. So let's say we have this is our going to be our boundary here, and so therefore the vector that is perpendicular will have w equal to the vector 1, 1. Okay, so this is my vector w here, and so here we can say, all right, this point is going to we're going to have w transpose x plus, in our case, we're going to have minus 4 equal to 0, right? And so this point here would be 4 comma 0. And so I would have W, I guess 1, 1, 1. So this is transpose, okay. So 1, 1 times 4, 0 equals 4 minus 4 is equal to 0, right? Here is the point 2, 2, right? And then so I can do, 1 times 1 comma 2, 2. This will also equal 4 minus 4. That will equal 0. Here is 0, 4. And all of these, going back over to here, I have negative 1, 5. And we can also see that if I do 1, 1 times minus 1, 5, and we want to do minus 4, this will also equal 0. So everything along this line satisfies this equation. Okay. Whereas if I picked something over here, what would happen if I put in 0, 0? So if I do 1, 1 times 0, 0 minus 4, I get negative 4. Right. So we're on the negative side. If I go over here to say 3, 3, okay, then W transpose X minus 4 is going to give me positive 2, right? W transpose X minus 4 equals positive 2. So this is on the positive side, and this is on the negative side of the boundary. And let me erase all of this. So this boundary is the set of points that satisfy the equation W transpose X minus 4 equals 0, where in our case W is 1, 1. Technically, this vector here. Okay, and then if I say we want W transpose X minus 4 equal to positive 1, I would get a parallel line like that. And then if I say W transpose X minus 4 equals negative 1, I get a parallel line like that. Okay, so we have these this would define the negative 1 and the plus 1 to define our nearest, or not, I guess, kind of some parallel hyperplanes there. Okay, and so what we want is we want to pick so that the closest points x1 and x2, which are going to lie on these parallel hyperplanes, okay, we're going to say W transpose X for this point plus B, whatever it is going to equal plus 1. For this point over here, any point along this margin will be W transpose X plus B is equal to minus 1. Okay, and so, this is a very simple where I have W equal to 1, 1. Obviously, for this picture, it's not going to be 1, 1. It's going to be slightly different, but, the W will give us a vector that indicates the direction here, and then what's the hyperplane is going to be defined by W transpose X plus B is equal to 0. This border here. Okay, and so we're going to find these points here, and so this purple, the vector that defines the margin, okay, can be found by taking the difference, the vector that defines the difference between 2 points that lie on this, x1 and x2, and it could be these 2 points, it could also be these 2 points, okay? because what we're going to do is we are going to dot that difference vector between x1 and x2 onto w. So we know w is in this direction, and if you dot the vector onto another vector, it's going to kind of give you that distance along that vector, right? So if we dot the, right, when you dot it, you're projecting one vector onto another vector. So we're going to do that, right? So the vector x1 minus x2 joins these 2 points, okay, the 2 points that exist along the margins, okay? And with the way the boundary is defined, w is a vector that's perpendicular to the boundary, and w divided by the norm of w is, a unit vector that is in the direction of that of this purple vector. Okay, so w over the norm of w is a unit vector in the direction that's perpendicular to the boundary. Okay, and we're going to just say 2 gamma is going to equal the length of the margin. So this distance, the length of this entire purple vector here, we're going to just set equal to 2 gamma. So what do I have? I've got w transpose x minus x2. Okay, so we're going to dot the vector with w over w norm here, and this will give us basically the length of the margin. Right, so when you dot one vector onto another, it tells you basically the length if you project that vector onto the other vector. And so this quantity right here, w transpose x1 minus x2 over the norm of w, is going to give us the length of this purple vector, and we're going to set that equal to 2 gamma. And so we want to maximize what this 2 gamma is going to be, okay? So if we want to maximize this, we'll distribute out the w transpose. I got w transpose x1 minus w transpose x2, okay? And I can add a minus b to both this and this, right? So I can say w transpose x1 minus b. This is equal to minus this w transpose x2 minus b. This is the same. And we know that w transpose x1 minus b is going to equal to 1 because x1 is on the positive side. And then we also know w transpose x2 minus b is on the negative side. So that's going to be equal to -1. So when I do that, I get 1 plus 1 over here. And so the distance, okay, gamma is going to be 1 over the norm w. That's how we get it here. So basically, because the norm of w is in the denominator, maximizing the distance gamma now becomes equivalent to minimizing this norm w. We want to minimize the norm w, and this is subject to the constraint that whatever w you pick, it has to make sure that all of the x values that are labeled positive stay on the positive side. All of the x values that are labeled negative stay on the negative side. So your w just has to be picked so that this condition remains true. Okay, and a clever way to kind of summarize to make sure that everything for x is positive is greater than 1, and everything where x is negative is less than 1. We're going to just take w transpose x minus b, and we're going to multiply it basically by the label, whether it's +1 or -1, and we're just going to say that that thing has to be greater than +1, because when it's positive, this thing is going to be positive, and this is positive, so it'll be over 1 here. When w transpose x minus b, when x is on the negative side, this is going to be negative, but its label is also negative, so when you multiply those, you're going to get a positive thing. So we're going to leave it there, and we want to minimize this. Same thing as minimizing. The value that minimizes the norm of w is also the same value that minimizes 1/2 the norm of w squared. Okay, and anytime you want to do optimization of a function subject to some kind of constraint, one technique is to use a Lagrange multiplier. And with a Lagrange multiplier, basically you have the objective function that you want to optimize. In this case, it's going to be we want to optimize either the norm W, or right now we're going to simplify things, we're going to norm 1/2 W squared. And we're going to add, basically little Lagrange terms for each of these constraints that we need to kind of keep, okay? So we actually have n of these Lagrange terms, okay? Basically, one for every single observation, because for all of these observations where we have a plus out here or a minus down here, the W that we choose has to respect that these points remain on the plus side and these points remain on the minus side. So, we can't just pick some W and say this is going to maximize it if things end up on the wrong side. So we're going to have a whole bunch of these Lagrange terms, one for every single observation. And so our objective function is we're going to try to minimize the norm of W squared. So the norm of W squared is equivalent to W transpose W, right? You're just, norm squared is just the sum of those terms there, okay? This is the constraint that T times W transpose X minus B has to equal or be greater than or equal to 1. So we're going to just subtract off 1. And here we have that constant for the Lagrange term, and we have n of these Lagrange terms in here. So this just gets kind of messier and messier. And it says, unfortunately, there's no closed form solution to this Lagrange multiplier problem, but apparently it can be solved using quadratic programming, and that's where it kind of leaves us off, okay? So I guess to get it into a form that can be solved using quadratic programming, we can explore this a little bit further. All right, so we want to kind of minimize this. At the minimum, the derivative of this function with respect to W and B are going to equal 0. So we're going to say the derivative of this with respect to W is going to be, this W transpose W becomes, the derivative of that is 2W. The 2 cancels out with the 1/2, so we have W minus. And then this whole thing, after you kind of expand this out, with respect to W, the B drops out, and we just have alpha transpose X. Okay, and so this is what we have. The derivative, we set that equal to 0, which gives us a solution. And we're going to say W is going to be equal to the sum of all of this. All right, and then if you take the derivative of this with respect to B, the partial derivative with respect to B, you're going to be just left with this negative alpha times T for all of these things. Okay. And don't worry about this page. It's just kind of crazy. But we're going to kind of take this solution for W and plug it in to everywhere we see W here. Okay, so this solution where we say, okay, we know this is where the solution has to exist. The sum of W is going to be the sum of alpha T X. That goes into here, and we have a W transpose W, so we have this kind of thing here, and we're going to plug that also into the W right here. And so you get this thing, and you get kind of a whole bunch of this stuff, and this is apparently the form that you can use quadratic programming to kind of solve for. All right. But one thing to note, all right, is that the solution is just a matter of finding what the alphas are. Okay, the solution to this problem, after you kind of replace all of the W's with this form alpha T N and X, it's a matter of finding out what the alphas are. Remember, the T's are the labels for the points. The X are the values or the locations of those vectors or these points themselves. And alpha is just, what do we weight these things? And it turns out, basically, for everything that's not on the border, the alphas become 0. And the ones that are on the border do get some kind of weight. Okay. And that's what we have. So at the solution, the support vectors, the X points that define the margin, will have alphas that aren't 0, whereas everything else that it doesn't really influence where that margin is, okay, have alphas equal to 0. So you can see that the W that results will be basically the sum of the x points that define this margin, okay? Either multiplied by a plus t or a minus t, and then multiplied by some constant alpha. Alpha will then be a measure of how much this one point influences the that margin W. And identifying W is a matter of finding the correct values for alpha. And again, I guess it's done via quadratic programming. One problem with our current form of the maximum margin classifier is that if you were to add some kind of point, the solution could end up becoming impossible, or just one individual point could end up having a strong influence on the boundary here. Okay, so let's see. Let me go back a few slides. Okay, we said this is the solution that we should use here. But what if I had put in a minus sign right here at this location? I don't know if I can. Can I do that? How do I draw? Type text. Can I just type in a minus sign? Okay. All right. Oh, I want this to be red. Okay, so there we go. So if I add a minus sign here, then what happens? Our margin now has to accommodate this one point, and now my margin will have to look something like this, right? So this one little point here will have a huge impact on how we draw our margin, okay? And if I somehow bring this point over here, okay, now there's no solution. Now there's no solution. We don't have a line that can separate blue from red, a single straight line, okay? So that's one of the issues with having the maximum margin classifier, where we say, okay, we're going to find all of the alphas so that this what's going on here? I don't know how to fix this. Okay, find the alphas so that these constraints remain true. Okay, what we can do instead is we'll have a soft margin, and with the soft margin, we're going to say that we're going to relax this constraint that says, okay, you know what? It doesn't have to when we do the sign times the border times x minus b, it doesn't have to be greater than 1 for every single point. Okay, some of the points can actually have this distance between the, okay, we said this was 1. Some points can actually be inside the margin. Okay, we're going to allow for that. Okay, and some points can actually be on the wrong side. We can actually have a plus on the wrong side there. Okay, and that would be if what is this, xi? Okay, if xi for that one point is something greater than 0, okay, then that point is inside the margin. And if xi is greater than 1, it's actually on the wrong side of the boundary. And so we're going to allow for that. We're going to allow for things to end up on the wrong side of the margin. And so when you try to fall for the solution or figure out the solution, we're going to put a cap on how large the alpha can be. So alpha is kind of how much influence one point can have on the location of the boundary. and we're going to say, you know what, it's not going to have a infinity boundary. There's a limit for how much, there's an upper bound for how much influence a single point can have on the solution here. And that's going to allow for margins or points to end up on the wrong side of the margin here. And that's fine. So that's the support vector machine where you are limited to drawing a straight line. And we're going to allow ourselves to have points on the wrong side of the margin every now and then. Okay. Obviously, we still want to try to find, optimize the boundary as much as possible, where we get the maximum number of correct classifications. One thing is, so we're saying we want to maximize this function. This is kind of how we're finding our vector W for this thing. And one thing we can do is we can replace this product between our x values. So we have an xm transpose xn. And basically, the way it's figuring out this margin is it's basically taking this inner product between all of the x vectors. So it's kind of like saying, okay, let's compare this point to this point, let's compare this point to this point, let's compare this point to this point, and it's kind of computing all of these different things, right? Because remember, the way we found this margin is we said, okay, these are the two points, x1 and x2, that are on the border, and they're going to define this. But when you have the entire series of points, you don't actually know that these are the two that are closest. So as it's searching for these things, it's going to have to test, this point against basically every single other point. This point, this minus sign against every single other point, and it does this for all data points that you have in your data set. And that's what we're seeing here in this xm transpose xn, is it's comparing every single point m to every single point n to kind of figure out which kind of 2 points and which 2 points are going to be the ones that are on the boundary. What we can do is we can replace this inner product xm transpose xn with something known as a kernel function between xm and xn. Okay? And what is a kernel function? Kernel is one of those words that shows up all over the place in mathematics, and they mean something different every single time. So you might have encountered the term kernel in some other math class, and it has nothing to do with the kernel we're talking about here, okay? Unfortunately, okay? And then, there's kernel density estimation, which has a different meaning of kernel, okay? So, yeah, it's just a kernel thing. In this case, what is a kernel? The kernel function? A kernel function is the inner product or the dot product, okay? Basically, here we're doing an inner product or dot product between xm and xn. We have xm transpose xn, okay? And basically, we're doing the same thing between point xm and xn, except for the kernel function, we plug xm into some kind of transformation function phi. So we have this point, we put it into a transformation function phi, and we do the same thing where xn, we put it into the transformation function phi, and then we take the kind of inner product between the transformed vectors. So let me kind of just show you an example. So we could have a function phi that takes a two-dimensional vector, x1 and x2, and it transforms it into a three-dimensional vector by just doing, it's going to keep x1, it's going to keep x2, but it's going to give it a third component, which will be x1 squared plus x2 squared. Okay, so we're taking a two-dimensional vector, plugging it into this function phi, and it turns it into a three-dimensional vector. All right. So if I have the points 1, 1 and 5, 1, okay, what the kernel function will do is we're going to transform the point 1, 1 using this transformation function. We get 1, 1, and then 1 squared plus 1 squared, 2, right? And then if I apply the transformation to this vector 5, 1, okay, we keep x1 and x2, the first and second values, 5 and 1, and then we get 5 squared plus 1 squared, and 26. And then as I say, okay, I want to do the inner product, or the dot product of 1, 1, 2 and 5, 1, 26. And so we're going to get 1 times 5 plus 1 times 1 plus 2 times 26, right? So this is 5 plus 1 plus 52. We get 58. So this is going to be the result. All I've done is I've taken my two-dimensional vector, plugged it into this transformation function. I did it for both of them. I take the dot product between these two things and we get a 58, okay? The equivalent kernel function is xm transpose xn plus norm xm squared times norm xn norm squared, okay? So I don't have to actually use that transformation function. I can just get the result, because I just want to get this result 58, right? And I can get that result by just using this function directly. I don't actually have to do any of the transformations. I don't have to transform 1, 1 into this vector 1, 1, 2, and I don't have to transform 5, 1 into 5, 1, 26. I can get this result 58 by using this formula, right? So if I do 1, 1, and 5, 1, okay, we know if I transform them, I get 58. Or I can just do xm transpose xn, okay, 1, 1, inner product 5, 1, okay, and that's going to give me 6. And then if I do xm, the norm of xm squared and the norm of xn squared, okay, the norm of xm is 2, and this is 26. And if I just apply it directly, I get the same value, 58. So we can get the same value just by using the kernel function directly, and I don't have to do this transformation. Why are we talking about this? Why would we apply a kernel function here? Let me show you this little video. I guess there's a commercial that we have to endure. Okay, so the reason why we are bothering with this transformation stuff is imagine you have data that cannot be separated linearly. So this is a very old video, 16 years ago. Oh, it says new HD version. Oh, let's see this. Oh, look at that. Okay, yeah, that's better. Okay, so here is, we have blue and red data, and they are not linearly separable. We can't draw a straight line that's going to separate the blue from the red. But what we can do is we can apply this transformation function, right? So we're going to use a polynomial kernel, and right now our data exists in 2D, but we're going to transform it into 3D by adding this third dimension to it, right? And this is, I think, pretty much the same kernel where we have x, the transformation for x and y is x, y, and then x squared plus y squared. Okay, the third dimensional component, the 3D component is going to be x squared plus y squared. And so basically points near the origin are low, and then points farther away go up, right? So we have the two-dimensional data, and then we are going to transform it using that phi function to transform it into a higher dimensional space. Okay, and so now that it exists in a higher dimensional space, we can now find a plane, okay, a linear hyperplane in this three-dimensional space that is able to separate the blue from the red. So when it was in 2D, there was no plane, no single straight line that was able to separate from the blue from the red. But now that we've transformed it into 3D, we have a plane in 3D space that is able to separate the blue from the red. Okay, and so we can look at that, And so this is going to be the boundary as defined by a plane in 3D space. And we can take that boundary, project it back down into 2 dimensions, and we can see that this will now separate the blue from the red. Okay? So again, we're taking our data, we transform it into 3D, and in 3D, we have a linear separate, right? We're just looking for the equivalent to align a plane that is able to separate the blue from the red. Okay? And then that defines a boundary that separates blue from red in the data. And so this was possible by transforming our data from 2D into 3D. Okay. There are a lot of possible kernel functions. So that was just an example for going from 2D to 3D, going from x, y, going x, y, and x squared plus y squared. Okay. There's the linear kernel, which doesn't do anything, doesn't transform it. Polynomial kernels. There's the Gaussian or radial basis function kernel, which is probably one of the most commonly used ones for SVM. Okay, and basically all of these things are taking our data, our original data in 2D, transforming them into a higher dimensional space, and then using those transformed vectors to figure out where the boundary should be. Now, one thing is that we don't actually want to, I could have, so one thing I could do is I could take all of my 2D data, I could apply this transformation function, and now I have 3D data, and we go through the process of finding this thing. But we can actually just use the kernel function to get our answer without having to do the transformations. And that's actually very important because the Gaussian kernel, or the radial basis function kernel, which is a popular kernel, it takes our 2D data, or whatever, your finite dimensional data, and it transforms it into an infinite length dimensional, or whatever, infinite dimensional vector. Okay? And it's like, what? How do you get an infinite dimensional vector? Well, the radial basis function, the kind of the equivalent transformation function, is based on the Taylor expansion of the exponential function, right? So what was that, 32b? You learned Taylor expansions, and so you can take the exponential function and you have this infinite series of things. And so maybe after the 20th term it doesn't really matter because they're really tiny, but there's technically infinitely many terms in this vector, and so you can't actually on the computer or in real life take your thing and transform it into this infinite dimensional thing. But if somehow you did, and you took the inner product between two of these infinite dimensional things, you will get a finite value, right? And that finite value can be found just by using the equivalent kernel function. So for the Gaussian kernel, you can just take the two vectors, x minus y, you plug it into this thing, x and y, and you plug it into this thing and you get a finite value. And that's the equivalent of taking x, transforming it into infinite dimensional space, y, transforming it into this infinite dimensional vector, and then taking the inner product. Okay. Similarly, over here, we transformed from 2D into 3D, and we took the inner product and we got 58. Or we could just use this equivalent kernel function, which takes our 2D vectors and just gives us the same result without actually having to do the transformations. And so that's what we're going to do. We're not going to actually transform the vectors. We're going to just say, we're going to use the kernel function, which will give us the result, this equivalent result of if we had transformed them, and then if we took the inner product between them. And so if we use that, we can again plug it back into kind of our, quadratic programming thing to find the boundary or the set of vectors that will separate this. Okay, and so when we employ that into some weird data set like this, okay, so here I have red points and black points here, and we want to try to find some kind of boundary that separates the red from the black here. Obviously, we cannot do it with a straight line. I can try, okay, and I can try to do it with a straight line. And I can say, you know what, we are okay with points ending up on the wrong side. And so we can, to use support vector machines in base or in R, you can load up this library E1071, and we're going to say, okay, Y is the classification. Is it class, +1 or -1? That's what the Y is. Okay, black or red is the classification, and then we have X1 and X2 as our kind of predictor variables. And we're going to say I'm looking for a linear kernel, and so this is kind of the best straight line separation it can do between our regions. Okay. With a polynomial kernel, it's trying to find. It's going to transform it into a higher dimensional polynomial space. All right, and so I can do degree 3, and I guess this is the boundary it tries to find. I don't know if the performance of that is pretty any good. Higher degree polynomials give you a little bit more flexibility, but it's still not doing a great job in my opinion. Okay, Probably the most popular one is the radial basis function, or the Gaussian kernel, which again is based on the transforming into an infinite dimensional space Taylor expansion of the exponential function. And there are kind of two parameters that you can assign here. So when you look at this Gaussian kernel, there is there's this kind of this gamma value, and I guess the Fourier transform. Wait, what is this? One way to construct. Okay, well, anyway, so you see these 5 functions, and it's transforming the whatever that is. Okay, but you have these two parameters, gamma and cost. Gamma will influence kind of how flexible the boundary is going to be, and cost will represent how much the boundary will try to avoid misclassifications. And so in your homework, I'm going to have you play around with different values of gamma and different values of cost, so you can see the influence that these parameters have on how the boundary is formed. Okay, so you can adjust the gamma, which is going to show how flexible the boundary is. So this is with gamma 0.5, cost equal to 1, and this is kind of the boundary that it forms. If I change the gamma, okay, I'm going to keep the cost at 1. I'm going to reduce my gamma to 0.1. A lower gamma means the boundary is less flexible. So the example I have here is, what if, let's say you have this printed out on a piece of paper, and I give you like a piece of string, and I say, take this string and draw a boundary, okay? And so you can kind of like take the string and line it up, and you can say, okay, here's my boundary. I've got red points up here, I've got black points down here, okay? This is my boundary here. Now, depending on the string I give you will determine kind of what your boundary will look like. If I give you a thin cable or a thin string, it's really easy to have like tight little twists and turns, okay? On the other hand, if I give you a fat cable, it's going to be really hard to have tight little turns, because this cable is resistant to having like tight little corners, right? And so gamma equal to 0.1 is kind of like having a fat cable that is really hard to kind of make tight turns. Here with gamma equal to 0.5, I can have I have a little bit more flexibility. And here's gamma 0.1, very little flexibility. The cable's very resistant to making kind of turns, and so you have only kind of smooth curves here. As I increase my gamma, I'm allowed to make more tighter turns. So here's gamma 0.3, here's gamma 0.5. Gamma equal to 1, I can now start having some real tight turns in here. Gamma 2, my turns can be even tighter, okay? Gamma equal to 5, now I can have really kind of twisty turns here. With gamma equal to 10, now I'm like, this is like mountain driving, right? You get these really tight turns, and it says, you know, you can only travel like 10 miles per hour, and you can make these really tight, twisty turns, right? Gamma equal to, you know, 0.1 would be like a racetrack where you're traveling 200 miles per hour. You can't have tight turns, otherwise you'll crash and explode. So, you know, or a big fat kind of cable that's really hard to twist versus over here, you know, now you have this really thin string that you can kind of wind around and have really twisty turns. So that's going to be gamma equal to 10. What is this, right? For the bias variance trade-off, here we're going to have lower bias, high variance with high gamma. Back here, we're going to have high bias, lower variance. Okay, high bias, lower variance on this side, lower bias, high variance. Okay. Here I'm going to keep gamma at 0.5, so all of these will have similar levels of flexibility, but here we're going to show you what changing the cost does. Changing the cost says, how much does our algorithm hate misclassifications? Okay, so here's our current boundary. My cost is set to 0.1, okay? And so, you know, I have these dots over here, and, you know, these black dots are on the wrong side of the boundary. These red dots are on the wrong side of the boundary. And, you know, right now our algorithm is just like, oh, well, I don't mind misclassifications. Cost 0.1 says a misclassification doesn't hurt me that much, okay? As I increase the cost, okay, now it's going to try to affect the boundary a little bit more. So it really, you know, all of these red points right here with lowest cost, it's saying, yeah, you know, that's okay. Okay, here with a higher cost, it's trying to avoid misclassifying these points. Okay, so it bends this. Here, as I increase the cost, again, it tries to avoid misclassifications. And as I increase the cost even further, so at cost equals 10, it's doing its best to avoid misclassification. So you can kind of see how it goes. Now, gamma equal 0.5, again, reflects like how smooth that the bends and the twists are, right? So here we obviously have tighter turns than we do back here, okay? But we're not getting turns as crazy or tight as this. This was gamma equal to 10, okay? But here, gamma is stuck at 0.5, but I'm increasing the cost, and basically we're saying we really want to avoid misclassifications as much as possible. If I have gamma equal to 2, which gives me more flexibility, okay, more flexibility. Here it is with cost equal to 0.1. I don't have a ton of misclassifications already, but as I increase the cost of a misclassification, now we're getting, you know, even tighter curves and boundaries, and it's really trying to avoid misclassifications. And now we see, you know, this kind of enclave appearing, or exclave, I don't know, whatever it is, appearing for the red dots that, you know, happen to fall in the in this region of the thing, and it says, okay, you know, we really want to avoid misclassifications here, and so we're going to give this kind of its own little red sector here when I have cost equal to 5. And so you can kind of see these things. With cost equal to 10, we actually get our own little segment over here for these couple black dots that are over in this red region over here. Okay, so that's what we have. Okay, so this is kind of you know, trying to illustrate how some of these different parameters interplay. Okay, and just a few more. Now I have a high gamma. High gamma already has, you know, a very flexible boundary, and here I've got cost equal to 0.1, and as I increase the cost, we can see, you know, so here it is. So here's gamma 5, cost equal to 10. This is kind of the borders and the regions it draws out. Okay, so look at this. Here's gamma 2, 10, and here is gamma 0.5, 10. Okay, so increasing the cost in all of these things increases kind of the, where the boundary draws. But again, the gamma is more in control of like how smooth. This is gamma 10. Okay, gamma 10 cost 1. And let me show you. Here's gamma 0.5 cost 1. And let's compare that to gamma 2 cost 1 and gamma 5 cost 1. So we can kind of see the effects of different gamma values and different cost values. And they have different effects, right? Increasing the cost also will be lower bias, higher variance. Decreasing the cost will be higher bias, lower variance. But there is a difference in how changing gamma and changing the cost affects the ways our boundaries are drawn. Okay, that is it for today. Let me give you your last view quiz answer. Last view quiz answer is the letter A. A as in apple. A as in apple is our last view quiz answer. And so we'll wrap it up here. I will have an online lecture on Friday at noon. I'll still have office hours on Friday as well, in-person office hours. If you want to take a look at your midterm exam, you got to come to in-person office hours. I can stick around for a few minutes today if you want to take a look at your exam. I do have to take off like 1:50. So, we really only have 10 minutes or so, but I can accommodate a handful of students. And then if you're watching on the video or something, and you want to see your midterm exam, you can come in-person office hours on Friday, and then I'll have Zoom lecture on Friday as well. Okay, that's it for today. Have a great rest of your day, and we'll see you on Friday.